is a really important lesson in this curve sketching unit. In this lesson, we're going to learn about the second derivative and how that relates to concavity. Up until now, hopefully you have a great understanding of the first derivative, and now we're going to extend our understanding of calculus and derivatives to look at the second derivative, which, if we read this first part here, it says the second derivative is the derivative of the first derivative. First derivative gives us the rate of change of a function at a point. Another way of saying that, it gives us the slope of a function at a point. And the slope of that function can be represented with a tangent line. So when I say tangent slope or slope of a function, it's meaning the same thing. The tangent line just represents the slope of the function at a point. So that's what the first derivative tells you. The second derivative is going to give us the rate of change of the first derivative. So another way of saying that, it's going to tell us how are the slopes of the original function changing. Or what I have written here, it is the rate of change of the slope of the tangent. So to sum it up, first derivative tells us the slope of a function at a point. Second derivative tells us how those slopes are changing. And hopefully you remember from previous lessons, if first derivative is positive, that means the slope of the function is positive, which means it's increasing. If first derivative is negative, that tells us the slope of the function is negative, which means it's decreasing. Let's look at, in this lesson, what do the signs of the second derivative tell us about the function? So in this discovery, let's start by looking at this degree 4 function. I've given you the equation and the graph, and let's find its first and second derivative. For the first derivative, let me just use my power rule, and I would get 4x cubed minus 6x squared minus 0. And second derivative, well, I just have to find the derivative of the first derivative, so use my power rule again, and I would get 12x squared minus 12x. And it says, when is the second derivative 0? So let's set that second derivative to 0 and solve. Earlier in the unit, we learned about how when the first derivative is 0, that's called a critical number, and it might represent a local min or max point. This lesson, we're going to be focusing on the second derivative, and when that's 0, what does that tell us about the function? So I'll set it to 0, and let me solve this. And I'll solve it by factoring. So let me common factor a 12x from both terms. And now I'll set each factor to 0 and solve. So set 12x to 0 and set x minus 1 to 0 and solve both of those equations I made. So I'll get two answers. My first answer is 0 and my second answer is 1. So I found two places where the second derivative is 0. And you'll notice on the graph, I have those 2 points plotted for you. When x is 0, there's where the function is. When x is 1, there's where the function is. Now, those are two important points that we're going to have to look at what key characteristic of the function happens at those 2 points. And that's what we're going to go through in this investigation here. So part B says, use your pencil to simulate a tangent line to the function when x equals -1. And remember that a tangent line tells us the slope of a function at a point. Basically, it's saying use your pencil to represent the slope of the function when x is -1. Okay, I have in Desmos the graph so that I can get Desmos to draw the tangent line for me, but you're going to use your pencil to represent the tangent line. So your pencil should look just like this purple line right now. It's touching the original function at an x value of -1. And then it says, drag the pencil slowly to the right, keeping it tangent to the curve, approaching x equals 0. So let me just highlight the section in the graph between an x value of -1 and 0. So you notice that changed to a green section now. And it says drag your pencil to the right, approaching x equals 0, keeping your pencil tangent to the curve. So what should happen is your pencil should look like what's happening to this purple tangent line that Desmos is graphing. And then let's answer some questions about what was happening to that tangent slope. Remember, tangent slope means slope of the function. While you dragged it from here to here. What was happening to the slope of that tangent line? So it says, what is happening to the slope of the tangent? Is that tangent above or below the curve? And what's the value of the second derivative at an x value of -0.5? Well, maybe that's the easiest thing to answer first. What is f double prime at -1/2? And you could just plug that into the second derivative equation right here. And I'll get Desmos to do it for me. F at -0.5. Notice I have Desmos giving me the value of the function, its first derivative and second derivative, at the x value I type here. So it tells me the second derivative at an x value of -0.5 is 9. So let me start by filling in that answer. Let's write f double prime at -0.5 is 9. Notice that's a positive number. Let's focus on that. We get a positive number. Hopefully by the end of this, you'll understand why it's positive based on the shape of the graph. Now let's comment on what is happening to the slope of the tangent over that interval. So as we move the pencil from the left side of the interval, so when x was -1, to the right side of the interval, when x is 0, what is happening to the slope of the function? And remember, the first derivative tells you the slope of the function. So at the start of the interval, the slope of the function is -10. Pay attention to that first derivative value. What's happening to that value as I move to the right? So it starts at -10, and then by the end of the interval, it finishes at 0. So what's happening? It goes from -10 to -8 to -6 to -5, -3, and then all the way to 0. So over that interval, what's happening to the slope of the function? Well, the first derivative values are getting bigger. It goes from -10 to 0. 0 is much bigger than -10. So the first derivative values are getting bigger, which means the slope of the function is increasing. The slope of the tangent, which means the slope of the function, is increasing. And hopefully now that makes sense to you why the second derivative is positive over that interval. Right, look at the second derivative values at any point in that interval. If we look at the second derivative values, notice the second derivative values are always positive in that interval, because the second derivative tells us how the slope is changing. So if the slope is increasing, that means the second derivative will be positive. And graphically, what's that always going to look like? It says, is the tangent line above or below the curve? Notice in this section, the tangent line is always below the function. It's always below the curve in this section. Or another way of saying that would be that the function opens above the tangent line. So I'll write it that way. The function is above the tangent line. And then I'm going to put in brackets. The correct terminology for that is we say the function is concave up. Okay, let's do another interval. It says drag the pencil slowly to the right, keeping it tangent to the curve, so same process, but this time moving it through the x value of 0. I'm going to change the interval we're going to look at. Let's do from like -0.5 to 0.5. That way we move through 0. So I'll do this green section right here. And as we drag it through that section, what is happening to the slope of the tangent? And what is the value of the second derivative at 0.5? Okay, well, let's do the calculation first. So we did f double prime at -0.5, and we got 9. I wonder what f double prime at 0.5 is. If we plug 0.5 into the equation of the second derivative, what's asked Desmos what we would get? Second derivative would be -3. Okay, it's negative this time. Okay, so notice our second derivative at that point is negative. And we'll talk about why in just a second as well. Now let's comment on what is happening to the slope of the tangent, so the slope of the function, as it moves through x equals 0. So I'm going to start over here when x is -0.5 and finish over here when x is 0.5. So I'm moving through the x value of 0. What is happening to the slope of the function? And remember, the first derivative tells us the slope of the function at any point. So pay attention to the value of the first derivative as I move from left to right through this interval. So at the very start, the slope of the function is -2. As I move to the right, the slope of the function, it's increasing. It's up to -1, up to -0.5, and it gets all the way to, the slope of the function gets to 0. And then look what happens to the slope of the function. It's not going to keep going up. The slope of the function is not going to go above 0. It's then going to start going back down. Goes to -0.1, -0.2, -0.3, all the way to -1. So the slope of the function between -0.5 and 0, the slope of the function was increasing. And then between 0 and 0.5, the slope of the function was decreasing. As we move through an x value of 0, the slope of the function, which I'll write as the slope of the tangent, stops increasing and starts decreasing. That's why at an x value of 0.5, the second derivative is negative, because at that point, the slope of the function is decreasing, right? After an x value of 0, the slope of the function, when I say slope of a function, the first derivative tells us that those values are decreasing, which is why the second derivative is negative. The second derivative values tell us how the first derivative values are changing. Just like how the first derivative values told us how the original function's values were changing. And if we're talking about graphically concave up and concave down, before an x value of 0, the function is above the tangent line, it's concave up. And after an x value of 0, the function is below the tangent line, it's concave down. Part D, I think we're going to do the same thing as part C, but it says as the tangent line moves through an x value of 1. So let's move it through an x value of 1. So I'll do that from 0.5 to 1.5. So let's highlight that section in green. So from 0.5 to 1.5. So we're now doing that green section there. What's happening to the slope of the tangent as it moves through an x value of 1? So before an x value of 1, what's happening to the slope? Pay attention to the first derivative. That tells us the slope. What's happening to those first derivative values? It starts at -1, and it looks like they're decreasing. -1.4, -1.6, and so on. And then when we get to an x value of 1, the first derivative value got all the way down to -2. That's the lowest it's going to get. Because after an x value of 1, watch what happens to the first derivative values. They start going back up to -1.9, -1.7, and so on, all the way to 0. So the slope of the function before an x value of 1 was decreasing, and then after an x value of 1 was increasing. That's why, if we look at the second derivative values, before an x value of 1, they're negative, and then after an x value of 1, they're positive. So what happens to the slope of the tangent as it moves through an x value of 1? The slope of the tangent stops decreasing and starts increasing. Okay, let's summarize our findings. How is the second derivative related to the original function? So the graph of a function we say is concave up over an interval if, graphically speaking, the function is always above any tangent line you would draw on that interval. And algebraically, if we look at the slopes of the tangent line, so the slope of the original function, which is represented with the first derivative, if over that interval, those are all increasing. That would mean that the second derivative is positive over the interval. So a second derivative being positive means the function is concave up, which means the slope of the function over that interval is increasing. It doesn't mean the function itself is increasing, it just means the slopes of the function are increasing. The first derivative is what tells us if a function is increasing or decreasing. The second derivative tells us if the slope of the function is increasing or decreasing. And then let's talk about concave down. The graph of a function is concave down over an interval if, graphically speaking, the function is below all of the tangent lines on that interval. And algebraically, if we were to calculate the slope of the functions over that interval, those slopes would all be decreasing. Therefore, the second derivative would be negative. So if the second derivative is negative, the function is concave down. And then just two more summary points here. A function is concave up if the second derivative is positive, so greater than 0 over an interval. And a function is concave down if the second derivative is negative over that interval. In the investigation we did, you'll notice that I had you move through an x value of 0 and through an x value of 1, and notice that those are places where the slope of the function switches from increasing to decreasing. Not whether the function is increasing or decreasing, but the slope of the function, right? Like, let's look at this interval from 0.5 to 1.5 again. Over that interval, the original function is decreasing the whole time. That's not what we're talking about. We're talking about what's happening to the slope of that original function. The slope of the original function in the first half of that interval is decreasing. Over the second half of that interval, the slope is increasing. So that point right there at an x value of 1 is a special point where the slope of the function switches between increasing and decreasing. That's called a point of inflection. It's a point where the function switches from being concave down to concave up. So right here, our blank, a point of inflection is a point in the domain of the function at which the graph changes from being concave up to concave down, or vice versa. What's the value of the second derivative at a point of inflection? Well, look, at an x value of 1, what was the value of the second derivative? It was 0. And same thing at an x value of 0. Here, the second derivative was also 0. So at points of inflection, the second derivative is equal to 0, or undefined. And for it to be considered a point of inflection, there has to be a change in concavity, which means the second derivative would change signs on either side of that point. But it's important to keep in mind, not all zeros of the second derivative are points of inflection. There has to be a change of sign. There has to be a change in concavity. So the second derivative has to change signs around that point for it to be considered a point of inflection. Just like how with the first derivative, when we found the zeros, the critical numbers, they might represent local max or min points, but not necessarily, right? We had to check the value of the first derivative and make sure it changed signs to make sure there was a change between the function increasing and decreasing around that critical number in order to classify it as a local max or min point. So if we find a zero of the second derivative, in order to classify it as a point of inflection, we have to make sure the second derivative changes signs around that point. And here's an example just proving to you that a zero of the second derivative does not always represent a point of inflection, right? If we look at this function, x to the 4, this function is always concave up. There is no change in concavity. The slope of this function is always increasing. But if we find the second derivative, and let me just do that quickly. First derivative would be 4x cubed. Second derivative, if I differentiate the first derivative, I would get 12x squared, and I have that written here. Well, when is that 0? If I set this to 0 and solve, I would get 0. That would tell us that this is a possible point of inflection. But actually, if we look before that point, if I were to draw a tangent line anywhere, the function would be above that tangent line, so concave up. And after, draw a tangent line, the function is still above that tangent line, so it's still concave up. So this function is always concave up, which means there are no points of inflection. So just because an x value makes the second derivative 0 does not mean it's a point of inflection. We call it a possible point of inflection. We have to test to see if it is or not. Another important thing I need to point out to you here is a function can change concavity on either side of a vertical asymptote. If we look at this function, the function is a hyperbola, right? It's got these two branches. On this branch in the bottom left here, that branch, the function is always concave down. The slopes of that function are decreasing. To the right of the vertical asymptote, in the top right here, its slope is always increasing, so it's concave up. So there is a change in concavity around the vertical asymptote. But there is no point of inflection here because the function doesn't exist at the vertical asymptote. So if we read this, it often happens that a graph has different concavity on the two sides of a vertical asymptote. However, because the curve is not continuous at a vertical asymptote, it can never have an inflection point there. We'll look more at those type of functions in the next lesson. Okay, the next thing I want to talk to you about is the second derivative test, which can be used to help check for local max and min points. Now, I know we said the second derivative is all about concavity of a function, but actually that's really useful in being able to classify a critical point as a max or a min. We learned in the last lesson how we can use the first derivative test, and let me just quickly remind you about that. This same function that we've been looking at the whole time, notice it has a local min at this point right here, 1.5, negative 6.7. We could figure out that that's a local min because at that point, so at an x value of 1.5, the first derivative is 0, which means it's a critical number. The function has a slope of 0 there. Before that point, the first derivative is negative, which means the function is decreasing. After that point, the first derivative is positive, which means the function is increasing. So if the function went from decreasing to increasing, that means at the point it was a local min. That's the first derivative test. Second derivative test might actually be a bit quicker. Instead of having to test values on either side of the critical number and then look at whether the function is increasing or decreasing based on the first derivative, all we have to do is take the critical number, so take 1.5, plug it into the second derivative, and see that the second derivative is positive. That means that the function is above the tangent line, which means it's concave up, which means that point would have to be the lowest point in that interval, which means it's a local min point. So that's what this says here. So if we want to classify a local max or min point, we find the critical numbers, the points where the first derivative is 0 are undefined, and then we plug those points into the second derivative and look at the value of the second derivative at each point. So if the first derivative is 0 at a certain value of x, we'll call that c. And at that c value, the second derivative is positive. That means that we have a local min because the function is concave up at that point. If the first derivative is 0 at some x value, we'll call that c again. And at that c value, the second derivative is negative. That tells us the original function is concave down at that point, making the point a local max. So the second derivative test, I think, is easier than the first derivative test, but it doesn't always work. Sometimes the second derivative test can fail. Now, if when we plug the critical number into the second derivative and we get 0, notice that doesn't meet either the conditions here. It's only useful if we get a value greater than 0 or less than 0. That helps us classify it as a min or max. If we get a second derivative value of 0 at a critical number, that could mean that the critical number is not a local max or min, but not necessarily. It could still be a local max or min value. We just have to say the second derivative test fails and then check the first derivative test. And x to the 4 is another example of that. If we look back to x to the 4, there's a critical number at an x value of 0, right? The first derivative is 0 at an x value of 0. If I plug that into the second derivative, I would get 0. But we can clearly see at this point 0, 0, there's a local min. So we would have to check the first derivative, see the slope of the function is negative before, positive after, so it is a local min. So when you're doing the second derivative test, if you get a value of 0 in the second derivative, that just means the second derivative test fails. You can't draw any conclusions from it. You then have to try the first derivative test. Here's just a summary page of everything we know so far about a function, its first derivative, and second derivative. It would be really useful for you to, pause the video as I scroll through this and look at each of the graphs and all of the comments about the graph. I'll just read through it quickly, specifically the sections on first and second derivative. Remember, the first derivative tells you the slope of a function. So when the slope of a function is positive, going up to the right, the first derivative is going to be positive. And these red sections shows you where the first derivative will be positive. Those are the sections where the original function is increasing. The blue section, first derivative would be negative there because the original function is decreasing there. And at these two green points, the first derivative would be 0 because the slope of the function there is 0. And imagine drawing a tangent line there, they'd be horizontal, therefore slope is 0. Second derivative, the red section, I'm showing you when the second derivative would be negative. Why is it negative there? Well, graphically speaking, because it's concave down. Any tangent line drawn would have the function below it. And if we think about what's happening to the slope of the function over that red interval, the slope of the function is decreasing, which means second derivative is negative. In the blue section, the slope of the function stops decreasing and starts increasing. So since the slope is increasing, that means the second derivative is positive. And graphically speaking, it means it's concave up. And at the point where the slope of the function switched from decreasing to increasing, that's where the second derivative is 0. And that's a point of inflection, where a function switches from being concave up to concave down or vice versa. And then this page just talks to you about how we classify a point as a local max or min point. To classify a point as a local max or min, we can use the first derivative test or the second derivative test. If we look at both of them, they both start with the same step number 1. Find values of x that make the first derivative 0 or undefined. After we have those values of x, we have to figure out, okay, on the original function at those values of x, do we have a local max, a local min, or neither? And there's two ways to do that. Either do the first derivative test, where you test values on either side of the critical number to see if there's a switch between signs of the first derivative. Or we could just take the critical number itself and plug it into the second derivative and see if the original function is concave up or down there. But remember, if the second derivative is 0, that means the test fails and you have to go back and do the first derivative test. So actually, let's skip to example 3. I'll come back and do an example 2 in just a second. Let's do example 3 first. It says, for the function below, find the critical points, then classify them using the second derivative test. So if I want to find critical points, I have to start by finding critical numbers, which are numbers that make the first derivative either 0 or undefined. So let me find the first derivative. That's a quadratic. It can't be undefined, but it could be 0. Let me solve for the values that would make this be 0. I'll solve this by factoring, so I'll common factor a 3x from both terms. And now I'll set each factor to 0 and solve, and I'll get 2 answers for x. I'll get 0 and 2. Since the question says we need the critical points, right now all we have are the critical numbers of 0 and 2. To find critical points, we need to plug those x values into the original equation and figure out the y value of each of these points. So we need the y values of each of those points. So we'll plug 0 into the original function and 2 into the original function and evaluate both of them. When I plug 0 in, I get 2. When I plug 2 in, I get negative 2. So our critical points are the points 0, 2, and 2, negative 2. And let me just label those for you. These right here are the critical numbers, and these right here are the critical points. So I know at those 2 points, there's a slope of 0. So I know at those 2 points, the tangent slope is 0, which means they could be local max or min points. Now we're not going to do the first derivative test. If I wanted to classify this point as a local max, I could see that before that point, the first derivative is positive, meaning the function is increasing. After that point, the first derivative is negative, meaning the function is decreasing. So the function went from increasing before to decreasing after, meaning that at that point, it's a local max. We could do that. Instead, what we're going to do is look at the value of the second derivative at that x value of 0, and notice the value of the second derivative is negative. That tells us that the original function at that point is concave down, which means that point must be at the top of the function in that interval, which means it's a local max. So let's take the x value of 0 and the x value of 2 and sub them into the second derivative, and that will allow us to classify the points as local max or min. So let's do the second derivative test. So I'm going to have to first find the equation of the second derivative. Well, that's not very hard. Just use the power rule. Differentiate the first derivative, and I get 6x minus 6. Now let's plug the critical numbers into this second derivative. So I'll plug in 0 and 2 and figure out if the function is concave up or down at those 2 x values. At 0, the second derivative is negative. That tells us the original function at 0 is concave down. I'll write CD, short form for concave down. Therefore, the point 0, 2 is a local max. The second derivative is positive when x is 2. That means at 2, the original function is concave up. Therefore, that critical point, the point 2, negative 2, since at that point the function is concave up, that means it's a local min. 2, negative 2 is a local min. Good, so that's how you do the second derivative test. Let's go back to example 2, where it doesn't ask us to find any local max or min points. So we're not going to be using any first or second derivative test. It instead asks us to find all the points of inflection and the intervals of concavity for this function. Well, remember, a point of inflection is a point where the function changes its concavity. And for it to be a point of inflection, at that point, the value of the second derivative is going to have to be 0 or undefined. So we're going to need to find the second derivative. So let's start by finding the first derivative. So 4x cubed minus 12x. Now I'll find the second derivative. I would get 12x squared minus 12. And now we need to use this equation to find possible points of inflection. It would be a possible point of inflection if I can find an x value that makes this be 0 or undefined. Well, it's a quadratic once again, so it can't be undefined, but it could be 0. I'll solve for when this could be 0. Let me just common factor out a 12 from both terms. Notice I have a difference of squares. So x minus 1, x plus 1. Set each factor to 0 and solve. And I get 2 x values, which could indicate points of inflection. Let me find the y values that go with each of those. So let me plug those into the original function. Let me figure out what f at 1 and f at negative 1 are. So if I plug 1 in, I'd have negative 10. And if I plug negative 1 in, I'd have negative 10 as well. And this is an even function, right? All terms are even. Therefore, I know on either side of the y-axis it's symmetrical. So this makes sense. So I have 2 possible points of inflection at 1, negative 10, and at negative 1, negative 10. So I'll call these possible points of inflection. In order to verify if they are points of inflection or not, I need to check, is there a change in concavity around these points? Let me just show you graphically what I'm talking about. So here's that function, and we've got our two critical points, and I've got those labeled in blue for you here, at -1, -10, and 1, -10. Is there a change in concavity around those points? Well, before an x value of -1, notice that the function is concave up. After an x value of -1, the function switches to concave down. And then after an x value of 1, the function switches back to concave up. So yes, those are points of inflection. And we're just going to have to test the values of the second derivative around those critical points to verify that there is a change in sign of the second derivative that indicates that there is a point of inflection. So to do that, we will make ourselves a table. I'm going to have to test an x value in each of the intervals I've created. So between -infinity and -1, I'll pick -2. Between -1 and 1, I'll pick 0. Between 1 and infinity, I'll pick 2. I'm going to have to test each of those values in the second derivative. See if the second derivative is positive or negative, and then comment on what that tells me about the original function. And then that will help me figure out if there are points of inflection at the x values of -1 and 1. So if I plug -2 into the second derivative, I would get 36, which is positive. That tells me the original function in the interval between -infinity and -1 must be concave up. So it must look like this. Notice between -infinity and -1, what's happening to the tangent slopes? What's happening to the slope of the function? The slope of the function is increasing over that interval, which is why the second derivative is always positive. So it's concave up. Between -1 and 1, is the function concave up or concave down? Well, let's plug 0 into the second derivative. I would get -12, which is negative. That tells us in that interval the function is concave down. So it looks like this. And if we look in that interval, yes, the function is concave down there. The slope of the function in that interval is always decreasing, which is why the second derivative is always negative in that section. And between 1 and infinity, I chose 2. Plug that in. Once again, I get a positive answer, which means the function is concave up. So notice there is a change in concavity around an x value of -1 and an x value of 1. At those 2 points, the function switches between being concave up and concave down. So these 2 points that we found as possible points of inflection are both actually points of inflection. So I can say POI at -1, -10, and another one at 1, -10. The question also asks us to state the intervals of concavity. So I should say, when is the function concave down, and when is it concave up? So the function is concave down between x values of -1 and 1. And the function is concave up if we have an x value between -infinity and -1, or between 1 and infinity. So I'll say when x is less than -1, or when x is greater than 1. Last example. Example 4. Sketch a graph of a function that satisfies each set of conditions. It says the second derivative is -2 for all values of x. What that tells me, it tells me that the original function is always concave down, since the second derivative is always negative. I know the function is always concave down. It says f prime at -3 equals 0. Okay, it means the slope of the function is 0 there. It could be a local max or a min point. Oh, and it must be a local max because the function's always concave down. So I know there's a local max at an x value of -3. Oh, and it tells me where the function is when x is -3. It's at 9. So when x is -3, the function's at 9. I know there's a horizontal tangent there. The slope of the function is 0. And I know it's concave down over its entire interval. So I know the function looks like this. And now let's just jot down here. It says f prime at -3 equals 0, which indicates there is a local max at -3, 9. And I know it's a max because the function is concave down at that point. B. F double prime of x is less than 0 when x is less than -1. Okay, so that means it's concave down when x is less than -1. F double prime of x is positive when x is greater than -1. Okay, so it's concave up when x is greater than -1. F prime at -3 is 0. That means the slope of the function is 0 at an x value of -3, which means it could be a local max or min. And since an x value of -3 is less than -1, which means, okay, at that point, the function must be concave down and have a horizontal tangent, which means it's a local max. Okay, so there's a local max at an x value of -3. At an x value of 1, there's also a horizontal tangent. At an x value of 1, well, that's greater than -1, so that means in that interval it's concave up. So it's concave up at that point with a horizontal tangent, which means it's a local min. So there's a local min at an x value of 1. So I need to draw a function that has this criteria. A local max at an x value of -3. So I don't know what the y value of that local max is. I'll just put it here. And a local min at an x value of 1. And once again, I don't know where that min is. I just know it has to be below where that local max was. So I'll put it here. And now I need to draw a function that was concave down before an x value of -1 and concave up after an x value of -1. That means there's a point of inflection at an x value of -1 because there's a switch in concavity. And once again, I don't know the y value of that point of inflection, but I know it has to be between the max and min, so I'll just put it here. And now I'll draw a function that's concave down before an x value of -1, so the slope has to be decreasing over that interval. And then the slope has to start increasing after an x value of -1, meaning the function's concave up. There we go. Notice concave down in that section, concave up in that section, with the correct local max and min points. Okay, that's it for this lesson. Hopefully at this point in the unit, you have now a good understanding of what the first derivative and second derivative tell you about a function.